Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be talking about relative standard entropies and what affects them. When we're talking about the standard molar entropy, we're talking about the amount of energy that is dispersed into that substance at a given temperature. So, for example, the standard molar entropy at 25 degrees is the energy that is dispersed in that substance at 25 degrees. And so this is going to depend on the number of what are called places where that energy can be put in the substance. And so, what are the factors that are going to affect these number of places, right? So, remember, when we're talking about places of putting the energy into the substance, we're thinking of things like, for example, if you're in a solid, then the only place you can put the energy is into the vibrations of the solid. So all you have are vibrational energy. But if you could melt the solid into a liquid, then some of that energy, you're now creating more places to put energy, because now you have the ability for the substances to move from place to place. You have locomotion or translational motion, and you also have rotational motion as well. So those are new places in which you can put the energy, right? So you've got rotational energy now, and you've got translational energy and things like that. So where the number of these places that you can put energy will affect the standard entropy. And so, what factors? There are other factors that are going to affect the number of places that you can put the energy. So, some of these factors are the state of the substance. Is it a liquid, solid, or gas? Molar mass of the substance. The particular allotrope. Is it like, so for example, carbon? Are we talking about diamond, or are we talking about graphite, right? The particular, oh, sorry, I read that already. The molecular complexity. How complex is the molecule, right? Is it a 2-atom molecule, a 4-atom, 5-atom? Is this a protein we're talking about? And the extent of dissolution. How dissolved is it in solution? And I'm going to talk about one of these at a time. So let's start with the state of the substance. What state of matter is it in? So we saw before that for a gas, you have a greater entropy when you are in a gaseous state versus a liquid state versus solid state. So, and that's because, again, you have these more places to put the energy. Because for a gas, you've got the particles are so far apart. This increases the number of places you could put the number of um, ways in which you can arrange the particles in energetically equivalent ways is increased when you have a gas versus a solid or a liquid. So here we have an example of a liquid water, which has a molar entropy of 70. And here you have gaseous water, which has a molar entropy of 188.8. And so gaseous water has more energetically equivalent ways to arrange its components, which is going to result in a greater energy dispersed, right? So because there's more ways in which to more equivalent ways, energetically equivalent ways to arrange your components, that's going to allow for more energy dispersal. So that's why we have a greater entropy, molar entropy for gases than liquids, and therefore more molar entropy for liquids than for solids. And so next we'll do the molar mass of the substance. Okay, so what about the next one? So molar mass of the substance. So here I have a list of the noble gases and their molar entropies, and you can see that as the as we go down the group, the size of the atom gets larger, the molar mass gets larger as you go down, and you can see that the molar entropy increases as well. And so, what is the reason for that? So, can't really get into the details of this, but briefly, we could say that the energy states that are associated, so the energy states associated with the motion of heavy atoms are more closely spaced together than those of lighter atoms. And this close spacing then allows for a greater dispersal of energy. And as we said before, entropy is what we mean by a greater dispersal of energy. So when we talk about entropy or a greater entropy, it means greater dispersal of energy. And so having these more closely spaced um, energy, where is it? States, these energy states are more closely spaced, allows for a greater dispersal of energy and therefore a greater entropy. This only is true. Oops, I forgot my E on true. This is only true for elements in the same state because differences in state have a larger effect on entropy than, say, the molar mass. So this is true only if we have these in the same state. So these are all gases, so you can see that the entropy increases. And so that is the effect of molar mass on molar entropy. What about the particular allotrope? Let's look at that next. Okay, what about the particular allotropes? So here we're at the third part. So the particular allotropes that we're going to be dealing with is diamond and graphite. So here we have carbon. Carbon can either be in its diamond form or in its graphite form. So both of these are pure carbon, solid, and diamond. And here we have the molar entropy is 2.4. And here you could see here that graphite, carbon in the form of graphite, which is solid. Again, we have the same state. So that's important, again, because state matters. Because here we said state of the substance changes or affects the places in which you can put the energy and therefore the entropy. But you can see that the graphite allotrope, the form of carbon in the graphite form, has more entropy. And so we can see that by the structure of diamond versus graphite. So here, diamond, in diamond, the atoms are basically constrained by chemical bonds in a highly restricted three-dimensional crystal structure. This is known as a network covalent solid. And what does that mean? It means basically the carbon atoms are all bonded to each other in a mesh form where each carbon atom is bonded 4 times to other carbon atoms, which are then themselves bonded 4 times, and so on. So there's this complex mesh of interconnected carbon atoms all bonded together. And so it's a very constrained solid of carbon atoms. And so very little places to put energy, not very much motion, very solid. And so if you compare that to graphite, in graphite, the atoms are bonded together in sheets. So you get these carbon atoms are bonded in circles, and you got these sheets of carbon atoms bonded in kind of like 6-dimensional holes or 6-dimensional figures. But it's kind of like chicken wire, if you will. So it's like a sheet of chicken wire of bonded carbons. And so the sheets are kind of stacked on top of each other. And because of that, they're not covalently bonded to each other, but they're held together by intermolecular forces. And so those are going to be weaker and they can slide. So this is like the pencil lead in your graph is graphite. So when you write with your pencil and you rub, that force that you're putting on it allows the sheets to kind of slide off and go onto your paper, and that leaves a mark, right? So this ability to move and slide past each other allows for more places to put the energy, which means more entropy. And so we can see that the entropy is larger for graphite than it is for diamond. What about molecular complexity? Let's deal with that next. Okay, so let's look at molar complexity. So here we have argon and NO gas, or so they're both in the gaseous state. And you'll see here that even though argon has a larger molar mass, and we saw just a moment ago that more molar mass means more entropy. And so here you'll see that argon has a molar entropy of 154.8, whereas NO gas has a molar entropy of 210.8. So even though NO is a lighter molecule compared to the atom of argon, because of the complexity of NO, it has a larger entropy. And the reason for that again is that a molecule, the more complex the molecule, the more places in which you can put the energy and therefore disperse the energy and increase the entropy. And so molecules generally have more places to put energy than mere atoms. And in addition to that, I would add to that the more complex the molecule, then the more entropy that molecule will have, because more complexity of the molecule means that more places in which to put energy. And so you can see that gaseous argon only has the energy in the form of translational motion. So you only got that translational motion from place to place. The atom can only move here and move there, right, in straight lines. Whereas the NO, that also has rotational motion in addition to translational, and it also has vibrational motions at higher temperatures, right? So if the temperatures are high enough, you get that vibrational motion as well. So there you see, with the different types of motion that are available to a molecule, you get more places in which to put the energy and therefore greater entropy. And again, I could show this with regard to less complex molecules compared to more complex molecules. The more complex molecules are going to have a greater molar entropy compared to less complex ones for the very same reason. All right, what about finally the extent of dissolution? We'll talk about that in just a moment. Okay, and finally we have extent of dissolution. So here, excuse me, we have an example of your potassium chlorate solid and potassium chlorate aqueous. Same substance, but this one is a solid crystal and this one is dissolved in water, where the ions can be separated and dissolved in the water. And so you can see here that for the solid crystal, it has a molar entropy of 143.1, but the aqueous solution has a molar entropy of 265.7. And so why is there a greater entropy here? Well, when solid potassium chlorate dissolves in water, all of that energy that was in the crystal, that was concentrated in the crystal, now can be dispersed throughout the whole solution, because what happens is that those ions can then be broken apart by the water molecules, and then they can be spread out until they are fully spread out throughout the solution equally in all parts. And so that dispersal of the energy is exactly what we mean by an increase in energy for the substance here. So since here we have that energy concentrated in the crystal, and here we have that energy kind of dispersed out throughout the whole solution, this is going to have a higher entropy, because entropy is the measure of how much of that energy is dispersed. It's a greater dispersal of energy means greater entropy. So those are the 5 different factors that affect the number of places that you can put energy. I hope this was helpful. I hope you enjoyed this video and learned from this video. If you did, then please like this video, hit that like button. Also, make sure you subscribe to my channel, hit that notification bell right up there, and also put a comment down in the comment section below and write me a question or say something nice. I like to hear from you. Thanks for joining me and have a great day.